Hello. So today we will talk about the Leetcode number 233, the number of digit 1. Actually, this is a hard problem, and it actually took me about 4 hours to finally figure out the algorithm and the behind equations to solve this question. So the question is that, so suppose you are given an integer n, and we would like to count the total number of digit 1 appearing in all non-negative integers less than or equal to n. This means that suppose you have a number 13, the output should be 6. So we would like to build a function that given input n, we compute this number of 1 in all the number that equal or less than 13. For example, could be 1, 10, 11, 12, and 13 that have these numbers which include some digit is 1, right? So if the input n is a negative number, so we can directly return 0 because it do not have any non-negative integers that less than this -1 or something like that. This n, if it's a negative number, then we can directly return 0. So let's give a brief analysis of how to deal with this question. So just to build a slide. So let's have a try of it. This is a question, and let's just give you a very simple example. So suppose the number is A, B, C, D, E with 5 digits. Suppose we just take this as a example to analyze the solution to this problem. And we would like to count the number of 1 in each digit from E to the tens to the hundreds to the thousands and also finally to the tens of thousands the, um, position. So suppose we are currently looking at E, the final one, right? So we would like to ask one question. So how many times that E equal to 1? Well, it depends, right? It depends if E is 0, suppose our input example n is in this style. So we ensure that the input E is with 5 digits because we are currently discussing this special case A, B, C, D, E. So A should not be 0 and B, C, D, E could be 0. Now let's talk about E. When E is 0, the examples can be divided into these types of smaller numbers from 1 to 11, 21, and finally to 12,301, which is difficult to pronounce. So let's look at the red numbers. It's actually range over from 0 to 1, 2, and finally to 1230. So since it's from 0 to 1230, it includes 1231 number of 1 at the east position, at this position, this green position. And we can count this number is actually ABCD times 1, which is 12,000, 1,231. Sorry, I may miss the mistake before. So it's 1231. And in addition, when E itself is 1, so suppose we are given this number, then the smaller or equal to this n numbers will be like from 1 to 11, 21, and finally to 12301, right? And it's from 0 to 1230. So this is a red number. And actually it's a 1231 number of 1 actually. It's again it's ABCD times 1. So in addition, actually we should consider about another one special case which is not covered by this sequence. It's 1, 2, 3, 1, 1. Actually, 3, 1, 1. This one is changed from 0 to 1 as an additional case. So the result will be like we have this number before and plus 1, right? Plus 1 is given by this number. So this we get this number as the answer. So when e is larger than 1, we actually suppose that it's 1, 2, 3, 1, 2. Then it's actually quite similar with this case. So it's the red number will range over from 0 to 1, 2, 3, 1, right? Unlike the equal to 1 case. So finally, we have this 1, 2, 3, 2 as a result. So we just gave a very brief hint here. So suppose we would like to find how many times that e equal to 1. We want to answer this question, then it actually depends on three conditions. The first is e equal to 0, the second is e equal to 1, and the third is e is larger than 1. So when it at these three conditions, they also depend on the higher number. When we get rid of e, ABCD is its higher number, and 0 is actually its lower number. Even though we know it's nothing here, right? Because e is already the lowest digit here, right? So we time 1 actually. We time 1, right? We time it to 1 actually. It's a first case. Let's look at the D case. For the D, actually, it also includes three conditions: D equal to 0, 1, and larger than 1. And suppose it's 0. We would also like to answer this question: how many times that D is 1? So we look at the cases, the smaller numbers. Suppose we are given 1, 2, 3, 0, 2. Then it could be a range over from 10 to 19, which includes 10 ones at the 10th digit, right? 10th digit. And the second will be like from 110 to 119. It also includes 10 numbers, and the 1 appears at the 10th digit. In this similar rule, we can range over from 0, 1, 0, 0, 1, 9 to finally 1, 2, 2, 1, 0, right? And 1, 2, 2, 1, 9, which are all smaller than this number, right? So the red number, we look at the red number, it range over from 0 to 122. So there are 123 groups. Every group will have 10 digits, will have 10 numbers, right? They have 10 numbers, 10 numbers, 10 numbers. So it's totally have ABC, which is 1, 2, 3, right? Count times by 10. So it's 1,230 here, right? And when D is 1, we actually can analyze this in a quite similar way. So what are the smaller numbers? The similar number of groups, right? Right? So the red number will range over from 0 to 1 to 2 actually. So we finally have this ABC times 10. But in addition, their numbers we have not count because these three numbers do not form a complete 10 number set. This is a 10 number subset, right? So it's actually includes three numbers. It's 1, 0, 1, 1, and 1, 2. The prefix are all 1, 2, 3, right? So there are three numbers. So it's e plus 1. It depends on the final e actually. So this is the second case. Let's look at the third case. Means that d is larger than 1. So when d is larger than 1, we actually can form another subset with 10 numbers, right? Before we could not form it because there are only three numbers in the final set. But currently we can because d is larger than 1. Now we know that the final one, the final subset is 1, 2, 3, 1, 0 to 1, 9, right? It's 10 to 19, right? So we can additionally form one subset This is important so that we know the final answer is ABC plus 1 with a bracket and the types term. So this is 1, 2, 4, 0. So we give a brief hint here means that when we check when we want to answer this question, how many times that d equals to 1 actually depend on three conditions and the higher number and its lower number, right? Three conditions, higher number. One is d. As all the three conditions, we know that it depends on the higher number. And when d is 0, it do not relate to e actually. When d is 1, it actually depends on the e plus 1. When d is larger than 1, it again do not depend on e anymore. So only when d is 1, it depends on the number of e actually. This is the second case. So a quite similar rule. Let's look at the C case. So again, we would like to answer this question: how many times that C equal to 1? This is a hundred digit, right? So C is 0, 1, or larger than 1, three conditions, and we have subsets. Currently now, the subset is not 10 anymore. It's actually 100 because we are looking at the digit of 100 digit equal to 1. So the subset will be from 100 to 199, right? So 1 appear here. And the second group will be like 1100 to 1199. This is the second subset. Suppose we are given this number is 12012. And finally, we know the final subset is from 11100 to 11199, right? So there, how many subsets are there here? So we know every subset have 100 numbers, right? Because it's 100 to 199, they actually have 100 numbers inside. So the rank number, we look at the rank number. It's actually range over from 0 to 11. So it's 12 groups, right? 12 groups, each group with 100 numbers. So it's 100 and 200, 1200. And when C equals to 1, actually we could not enlarge the number of group. It's similar group, means that it's AB uh, times 100 totally. But in addition, there are actually 13 numbers left which could not form a complete 100 subset. It's from 100 to 112. So there are 13 numbers. So it's actually DE plus 1, DE plus 1. D is 12, right? DE plus 1. And let's look at the C larger than 1 case. Now we actually could form additional complete subset with 100 numbers. So this one are okay, but the final one is start from 12. It's 12, 100 to 12, 199, right? Because all these numbers are smaller than the given input. So it's from 0 to 12. Oh, this one is actually not correct. It should be from 0 to 11, right? This is should be 11. Okay. And now it's actually 13. It's 13 times 10, 100. It's actually 1,300 now. So we know um, we should always times 100 now, and when we count about C, it depends on AB and D actually. When C is 0, it only depends on AB. It's AB times 100. AB times 100. When C is 1, it actually depends on DE now. So not only include AB times 100, but also include the D plus 1. The D plus 1 means that this partial, not complete subset with 13 numbers. Finally, when C is larger than 1, we actually can build AB plus 1 subset, every subset with 100 elements. So we have the result is AB plus 1 times 100. It's 1,300 now. So we look at the D case, the B, a B case means that the thousand position here, B. So the question is the same. How many times at B equals to 1? How many times means that the number of numbers, which is equal or less than the input number n. So in addition, it's three conditions. Same way, so B is 0, B is 1, and B larger than 1. So currently the subset is not 100 anymore. It's actually 1000 because we are care about the thousand position digit. So when it's C case, it's 100. When it's D case, it's 10. When it's E case, it's actually 1, the subset. So now it's from 1000 to 1999. So there only one group. We cannot form the 11000 because it's already larger than this one input. So we only have one, right? One group, one subset. So it means that it's 1 times 1000. And let's look at the b equal to 1 case. So currently, again, we can only form one complete subset with 1000 numbers. It's from 1000 to 1999. So it's the same with this case. And in addition, there is a not complete subset from 1000 to 1033, 233, right? So this actually depend on the CDE now, depend on the number behind or lower than this current 1000 position digit. It's 234. Sorry for my poor pronunciation of numbers. So it's actually 235. It's CDE plus 1, right? Is it clear? Now when B is larger than 1, actually we can in additionally form one subset with 1000 elements. It's from 0 to 1 now, which is 2 times 1000. It's A plus 1 times 1000. I think till now the rule will be very, very clear. But just let's look at the final A case, the left hand side boundary. So same question. So how many times that A equal to 1, right? How many numbers included in this equal to or similar than or smaller than the input n case? When A is 0 is not possible because we would like to ensure that is a 5 digit here. But if A is 0, we would like to ask for BCDE case, right? It's we already discussed BCDE case. So we just skip this case and we look at how about A equal to 1. Suppose our input is 1, 2, 3, 4, 5. So it do not have any higher digit, right? It's 0. It do not have any higher digit. So it's 0. We only need to care about the lower digits. The lower digits. So the number of subset with a size of 10,000 is 0. There are no this kind of subset. And we need to count on these lower numbers. It's BCDE, right? So this is a not complete subset. It's from 10,000 to 12,345. It actually includes 2, 4, 2, 3, 4, 5 plus 1, right? These numbers. And when A is larger than 1, we actually can form one subset here, right? It's with 10,000 numbers. So it's this one. So it's 0 plus 1, 2000. This is complete because we only care about the 10,000 digit here, right? So when it's 2, there is no this such kind of numbers. So we only need to care about this subset, which is 0. 0 is a higher number, and 1 with plus 1, right? Plus 1. And it times the subset size, which is 10,000. I think till now, until the fair analysis, we know that when we want to count the number of 1 in one digit, we need to care about 3 conditions. A is 0, 1, or larger than 1. And also we need to care about 3 positions. It's higher number, it itself, its current number and its lower numbers, right? So the conclude is like this. The generally for one digit current number x at position, it have a position, right? So before a is at actually at the position of 10,000. It's 10 with a power of 4, right? And b is actually at the thousand digit, so it means that it's 10 with a power of 3, right? Thousand level. And the c is 100. It's a 10 of power of 2, and d actually y is 1, right? And y is 0. So for one digit number x at position 10 with the power of y, the 1 at that digit is right. Well, x is three conditions. When x is 0, it's dependent on its higher number times 10 with the power of y. When the higher number is 0, it's actually 0. When x is 1, it's dependent on two things. The higher number times 10 with the power of y plus its lower number plus 1, right? It's from 1, 0, right? We know this case, right? It's e plus 1, d plus 1, cd plus 1, and bd plus 1. And finally, when x is larger than 1, we know that we can complete one additional subset with a size of 10 power y, right? I think till now the idea is very clear. So for example, let's look at the code. So this is my code. I think it's rather easier to understood. So initially, if n is 0 or smaller than 0, we return 0, right? Because when I wrote this code, I forgot this line. Actually, there is a test case of n equal to minus 1. It's bad. So the count, the finally count. And we have a factor. The factor is actually 10 with the power of y. Initially, y is 0, so factor will be 1. And every loop, we times it with 10. So initially is 1, and after one loop of while, it will be 10, 100, 1000, and so on. So we will have three numbers that count the lower number, a current number, and its higher number. Initially, they are 0. So we have a loop, and condition is that n divided by a factor is not 0. If it's 0, means that the highest digit is already less than the factor. So we do not need to go into the loop anymore, right? For example, if n is 2 and I factor is 10, we divided, actually it's 0. So because it only have one digit, we do not need to care about the 10, the 10 condition, right? So we compute its lower number. So we first divide it by a factor, and then we time a factor. We minus it, we get its all the lower number, right? And the current number is easier, right? We just divide it by a factor, and we got the mode of 10. The higher number is that we divide it by a higher factor. If current I factor is 1, then we divide it by 10, right? Then we get the higher number. So three conditions. If it's 0, we plus it with the number of factors and the number of subsets. This number of subsets, and this is the size of that subset, right? It could be 1, 10, 100, and so on. When it is 1, actually, the subset is the same, but we need to care about the lower number. It's plus 1, right? When a current number is larger than 1, actually we have another additional subset with a size of I factor. So we update these three conditions and sum up I count. Finally, we return the I count, right? Okay, we try to, let me see. We try to, where is it? Okay, we write it, the code here, right? And we know that first, if n is smaller or equal to 0, we return 0. So now we have I count is 0 and I factor is 1, and we have I lower num, I current num, and I higher num 0, 0 and where what will it an I factor it's not 0. What should we do? We should compute the three numbers. What's it? It's like n minus oh n divided by I factor and times I factor. Second is I current number. It's what's it? It's only one digit now. It's n I factor with a mode to 10 and I higher number. It's very simple. It's I factor times 10. So three conditions. If I got the number is 0, then I count should be plus equal to what? Should be I right, it's correct. I count it is 1, then it's the same I factor and plus. But it's I lower plus 1, right? And the final case that means that I count number is larger than 1, so we have another additional subset plus 1 and times I factor. So finally we need to update the factor. I return I count. Okay, let's try to submit it. Run the code, have a test. Okay, it's correct. Let's submit it. Okay, it's fine. 33 ms. Okay, fine. So that's it. So if we'd like to briefly conclude, it's like this one. So just three conditions, right? 0, 1, larger than 1. And for every digit, we consider it's actually three things, right? Current digit with three conditions, it's higher number, it's lower number, right? These numbers are not only limited to one digit. It could be 0 or more. It's or more. It could be quite large, right? So I think that's it. Thank you.